Yeah, I mean, the idea of collecting information, seeking patterns of that information, those are all themes that I'm going to talk about today. But I want to take it to sort of the next level is once we have those patterns, can we mine them for some information that can help us make better decisions in a planning context? And largely, this book is about using data to help make better planning decisions, although I'm going to try to cater my comments today to planning around climate change. Obviously, I think it may be a little more apropos. So I am delighted to be here. Thank you so much, Coco, for having me and to come chat with the team. My name is Ken Steiff. I am the sucker with two full-time jobs. First, I direct the Master of Urban Spatial Analytics at the University of Pennsylvania, which is a graduate program at the intersection of data science and public policy. My other second full-time job is running a comparable consultancy that tries to build open source analytical tools, mostly for governments, but we work with a variety of stakeholders. And it is worth mentioning for the other entrepreneurs in the room that giving away your software as free and open source is really a terrible business model. But it does allow for the kind of social impact that I am personally after. The software that we write is being replicated in cities, counties, and states across the US, which, you write it once and everyone uses it. That doesn't pay well, as I said, but it is an important success measure for me. Open source is very important to me personally. So here is what I'm going to talk about. The big thing we're going to talk about today is forecasting, and again, in a planning context. And forecasting in a planning context, and specifically in a climate change planning context. To start, really, I think the impetus of this talk is that I wrote a book, which is really a shocking outcome for someone like me. So, of course, I'm going to talk about that. I hope to provide a bit of a framework about why not all forecasting models are created equal, and some may be better suited for planning, and I'll give you some examples of that. And here is the book. It is called Public Policy Analytics. As you can see from the subtitle, it includes code and data for those of us who want to learn how to actually build these tools. It's written in the R language. And it also includes context for non-technical policymakers about how to think about data science and algorithms as tools for delivering government services. The book is really based on the premise that data science in government is much harder than it is in business. So in business, if an algorithm makes us more money than what we were doing before, awesome. That's just how we do things from here on out. In government, we have to optimize for many disparate and much more nuanced bottom lines. Bottom lines like equity and fairness, politics, bureaucracy, and so much more. You can imagine those ideas, equity, fairness, politics, etc., those are not as simple to optimize for as revenue. And that means building data science tools in government is much more difficult. And frankly, that level of complexity is what draws me to it. So the book will be published in July. It's on CRC Press, but it's also open source. You can see the QR code here. If you scan it on your phone, it will bring you to the open source version of the book. It's fully reproducible. The code and the data is there. Take my word for it, it looks beautiful on mobile. I mentioned now 3 times open source is important to me. This book initially was written over the last few years to serve my fall class. And so this is basically the book that we use in that class. And now I'm obviously delighted to make it open to everyone. And then I think the last big theme of the book that's really important, and I won't really touch on it in this talk, but there's a framework that's built in the book to help policymakers try to trade off the utility of an algorithm, and its ability to deliver a service with fairness. And algorithmic fairness is something really important in this world and something I spent a lot of time discussing in the book. And this framework about trading off utility and fairness, I call that algorithmic governance. But again, I won't talk too much about that in here, but I want you to know that that is an important theme of the book that I'm particularly proud of. All right, so let me jump into it. The idea of prediction and forecasting is not new to city planners. I'm a city planner by training. That is my PhD. That's how I identify professionally. Throughout history, city planners have made ill-fated forecasts into a very uncertain future. And this is one of my favorite examples, the 1925 plan for Cincinnati. It's one that I highlight in the book. Cincinnati, up until this time, had experienced unprecedented, incredibly rapid growth during the Industrial Revolution. And of course, for them, they just assumed the party wasn't going to end. This was always going to be the case. So as part of their comprehensive plan, I really love this, the authors wrote that population forecasting is, this is the quote, the obvious basis upon which scientific city planning must be formulated. So predicting population over the decades to come is the obvious basis upon which scientific city planning must be formulated. And what they did was to make the assumption that historical growth would continue or generalize long into the future. And this idea of generalizability is going to be a key theme that I'll discuss with you today. And as you know, of course, in reality, a Great Depression, suburbanization, deindustrialization, these huge structural issues caused the city's population to fall nearly 70% below its 1950s peak. I know, shocked, right? This is a forecast gone terribly wrong. And so here's, I think, the point. To reasonably assume that Cincinnati's past would generalize to its future and allow us to forecast population appropriately, planners of the day would have to understand how really complex systems like housing markets, labor markets, credit markets, immigration, politics, how all of those systems interrelate. And if those systems were understood, like population forecasting would be a layup. Not only could we forecast population, but we would know what, levers to pull to bring, health and prosperity to us all. But, in case you didn't know, we are far from such an understanding about how these complex systems interrelate. And I guess the bottom line is that with these systems that I mentioned, there's just too much uncertainty to develop reliable forecasts decades into the future. All right, so these forecasts about decades in the future, forecasting in really complicated interrelated systems, these kind of forecasts are obviously really difficult to accomplish. Now, I am not a climate scientist, obviously. I am firmly and very confidently a social scientist. I imagine, I think, from what I can gather, climate scientists have a better idea about how interrelated climate systems, like some shown here, how those systems interrelate. And that helps certainly with the uncertainty issue. But again, when forecasting in these systems 30, 40, 50 years out, there is still a lot of uncertainty. And the example I want to focus on for the next few minutes is something like climate migration, which is a really interesting subject for me. So to plan when and where climate migrants are going to show up, we need to marry climate forecasts with the kinds of social and economic systems and forecasts that I just mentioned. And blending those two, I think, is exceptionally difficult. So while climate change planning does rely on climate science, I think, in my opinion, if we're talking about how to build planning tools in response to climate change, then an understanding of these social and economic systems are also crucial. So I know this is a bit cryptic, and let me delve a bit further on this example. The New York Times ran this really terrific small series, but just awesome journalism in the summer and fall of 2020 on climate migration. And I love this question, the question they asked, because it is very much a forecasting question, and it's so much of a traditional planning question. Millions will be displaced, they say. Where will they go? I love this question. The where question, as you will see, much of my work is geospatial. So like this where question, it's like, it is just the perfect question for me. As I will show you, it doesn't, answering this question, where will they go? It actually involves not just one forecast, but many forecasts. And I think the authors provide some really compelling anecdotes. I'm just stealing some of the data visualizations, beautiful data visualizations from the article. They show 3 domains that are important for understanding this climate migration question. They talk about disasters like wildfire. They talk about sea level rise and crop suitability. And for each of these, they show maps of the affected places here. These are counties, and forecasts on the number of people who may be affected. And I would add a 4th critical domain, which is risk to aging infrastructure, systems that nearly completely failed in recent weeks in Texas and in other places. And this continues to happen, infrastructure failing. And keep in mind these very expensive infrastructure projects. They are financed by a municipal bond market that is still struggling to understand how to capitalize climate risk into their assets and their investments. And so ultimately, I think there's a really important planning question here, which is how can we predict or forecast those places that will be unlivable and those places that will be livable? And if we knew this information, what do you think different stakeholders would do about it? And I have to tell you, like once a year, probably, over the last 3 or 4 years, I have these calls with these very fancy pants hedge funds and REITs and real estate investors who all want me to build them these forecasting tools to help them make long-run investment decisions about regions in the United States that will be resilient to climate change. So real estate investors are a massive player here. Again, municipal bond investors and other financial institutions have a huge stake in this question. And then obviously, my favorite stakeholder, government. Government has struggled, excuse me, at least the United States government, with comparable issues. I just want to remind you that in America, climate migration is not completely unprecedented. Post-industrialization really removed the reason to be for many towns and cities in the American Rust Belt. And we, government, we taxpayers still invest in those places and do not and have never really had a good plan in place to incentivize people to move to more productive regions. And this is a similar problem that government will face when it comes to climate migration. So I want to talk about what it might take to answer this question of which places will be desirable for climate migrants. So I come from an economics background, and I often like to break things down to supply and demand. And I'm sorry if that is offensive to you, I completely understand, but I'm going to go ahead and do it anyway. On the demand side, the question really is how many people will migrate, from where will they come, and most importantly, when will they do so? And this, I would argue, is the really hard forecasting question because many super significant assumptions have to be made. Can climate models pinpoint where and when regions throughout the world will become uninhabitable? What is the lag time between a critical mass of migrants before a critical mass of migrants decide to depart to seek greener pastures? And again, if we have to forecast this 30, 40, 50 years into the future, it's a tremendous amount of uncertainty. But on the supply side, on the bottom part of this slide, these forecasts are the ones that I focus on and I believe are a bit more manageable. Assuming that institutions like the ones that I mentioned liberally respond to new demand for housing, that is in places where migrants are going to show up. And maybe this is because of growth coalitions or just the lure of new property tax revenues, then I think it is possible to forecast areas that could develop next. And I'll illustrate that just in a few moments. And I also think it's reasonable to forecast things like crop suitability and really carrying capacity, land use issues. I just have to tell you, I have this brilliant fake startup idea about using a whole bunch of climate and soil data to try to figure out when Napa and Sonoma, two of my favorite regions in America, when they no longer become the winemaking region of choice because of climate change, where will the next region be? And if you can figure that out, you can basically cash in on the future value of that agricultural land. Well, of course, that's not just about fancy winemaking or growing grapes, but pretty much for every crop in America, where in the world, where will be the next place suitable to grow that crop when these growing conditions shift. So before I give you a couple examples, I want to briefly present the framework that I use or that I develop in the book that suggests why some of these supply side forecasts are a little more manageable than this big one on the demand side, where we try to forecast decades into the future. And I told you just a few moments ago that these multi-decade forecasts are less reliable. And I told you that because we shouldn't assume that the past will generalize 30, 40, 50 years into the future. So which phenomena might reasonably generalize? And I think, you know, the words here are really the goal of a useful planning forecast, at least as I see it. The goal is to borrow the experience of people or places where outcomes have already occurred, and then test the extent to which those experiences generalize to people or places that have yet to experience that outcome. And this is not trying to test this generalizability over the decades to come. I'm not really even talking about forecasting across time at all. It's more cross-sectional. I'm talking about borrowing the experiences over here in this part of the country or the world and predicting those outcomes over there in a different part of the world, while only changing small bits of the system. And the example I want to give you, just to start, I think it's a really salient example. It's not about climate change, but I think it will hit on how this relates to planning, and it will show you the cross-sectional nature of this kind of forecasting. This is a very planning-oriented use case that I did back in 2013. And the question that I wanted to ask is that in cities with bike share systems, of which in 2013 in the US there weren't many, in cities with bike share systems, are ridership patterns sufficiently general enough that they can be used to predict bike share usage or bike share demand in cities without such systems? So the idea was to take bike share trends from New York, Boston, Chicago, and Washington, D.C. to predict for my city, for Philadelphia. Now, when I set out to do this, this was nearly a year before Philadelphia's bike share system debuted. And the way that the system at the time, the way bike share, and currently, frankly, the way that we design bike share systems, specifically where do we put bike share stations, is very oversimplified. It's really more of a design exercise than one based on evidence. Now, hopefully I can convince you that the behavior of bike share riders is relatively uniform across most cities. The goal is to get from point A to point B for work or leisure, and do so by minimizing friction. So if we were faced with Route A that was relatively flat and Route B that was like a massive hill, most people, you know, all else equal, are going to take Route A. And if I can convince you that this behavior of bike share riders is relatively uniform across most cities, then the idea is that I can use these observed bike share experiences from those 4 cities to test whether they generalize in a forecasting context. And if they do, then I think they can reasonably be used to forecast bike share demand in a city like Philadelphia, which, as I said, at the time, did not have any bike share. So for the modelers among us, the way this works was that I took trip counts for the first 4 months of these systems' existence. I aggregated them to the census tract level. A census tract, for those of you who don't know, is a spatial unit that's almost like a neighborhood. Gathered a bunch of predictive features or independent variables to try to explain the variation in trip counts across these neighborhoods. And the question was, did the experience in my what we call training set cities, that's Boston, Chicago, New York, and Washington, D.C., did they generalize to Philadelphia? And so if you look at the plots on the top left, these are distributions by cities. Features like total population, or tot pop, and percent female, p female, all have similar distributions across the cities. While on the top right, percent of residents commuting by car, that's p drive, they're a bit more all over the place. It may be that variable may generalize a little bit less. And as you can imagine, here I'm only using experiences from 4 different cities to predict for Philadelphia. But the more experiences I have, in other words, the bigger the data set, the more I have to generalize from, and likely the more accurate the forecast can be. All right, so here is the punchline. The forecast predicted 276,000 bike share trips in the first 4 months of Philadelphia's bike share system. Fast forward it, a year and 4 months when the bike share system actually debuted. In reality, what I predicted was just 17% more trips than actually occurred in the first 4 months, which is a pretty good forecast. Particularly, we only used 4 cities worth of experiences. And in other words, I think the way you can think about it is that bike share experiences in those 4 cities absolutely did generalize to Philadelphia, which effectively, it allowed for an effective forecast. And you should consider that bike share is not this like boundless system or even interrelated systems, as I mentioned, like housing markets and labor markets. It's pretty closed. It's not marred by great uncertainty. The people making decisions, bike share riders, all have the same kind of motivations and behaviors. There are some shared experiences that underlie bike share demand. And the forecasted demand, you can see them on the map there. We forecasted at a very small geography, the census tract or neighborhood. And these forecasts could be used by bike share planners in Philadelphia to decide where to allocate the limited bike share stations they can actually afford to put up there. And in other words, this is a planning tool. And of course, you didn't have to use this in Philadelphia, but I wanted to make the point at the time that this could be used for planning around the country. And so what I did was to design a wireframe for a website where a community group or a nonprofit or a city planner could upload the required data, and the algorithm would basically stamp each census tract or neighborhood with a predicted measure of bike share demand, the number of trips that would originate from that area. The user could then do a very simple back-of-the-envelope cost-benefit analysis to try to understand how feasible a certain bike share network configuration could be. And this is a beautifully simple planning tool that could be deployed basically for any community in the US or frankly anywhere in the world that wanted to do bike share planning. Now I know this use case is a bit of a digression, but I do think it's a simple enough one that tries to prove out this idea of borrowing the experience over here in these 4 cities and predicting over there in Philadelphia, right? I'm not predicting way off into the future. It's cross-sectional, it's geospatial. And I want to return to a couple examples that relate to climate change. I guess what I want to try to get you to think about are, what are some of the experiences related to climate migration that could reasonably be generalized or forecasted? And how could some of these forecasts make for some useful planning tools? And I'm going to give you some examples from my teaching, from my own work. I'll give you 2, just like what I just did, smaller case studies, and then a few other examples that my students are currently working on, or examples that others should be thinking about as well. But for the most part, I'll try to run fairly briskly through them. I could talk 45 minutes about each of these, particularly next 2 use cases. And I want to start with a case study in Houston, Texas. Now, I know Houston is obviously not a place where climate migrants will flock in the future, but that fact notwithstanding, there are what I want to try to impress on you is that there are some very specific patterns in how Houston has developed over the decades. And all cities, particularly cities in market economies, develop with a very predictable pattern. And mostly, again, because they are market cities. And in this use case, the goal is to mine those patterns, those development patterns or experiences. In this case, we're looking at three predictive features: population change, these are the maps on the right, population change, access to transportation or highways, and proximity to existing development, among many other features that we use to ultimately try to predict, the map on the left, new development. This is basically new development over the course of a decade. And I'm skipping, you know, like a couple thousand lines of code and a tremendous amount of economic intuition and otherwise. But from this kind of model, what we get is the ability to forecast a distribution of predicted development probabilities. That's the map on the left. Those development probabilities are interpreted as the probability in this location that development would occur here. And again, the way this is done is by developing or mining the development patterns from the past to predict development suitability or development probability in the near future. In this case, you can really see how access to highways is an important predictor. The darker the blue, the higher the probability, and it's really, you know, the closer we are to highways, the greater that probability. And I think even more interesting is we can see how that predicted development suitability really clashes with environmentally sensitive land. So, you know, this is sort of, you don't see this here, but develop some measures for identifying environmentally sensitive land. And the map on the right illustrates development potential overlaid with environmentally sensitive land. So this forecast here uses the National Land Cover Database, which is only for the US. But I want to mention there are other resources that would enable similar forecasts really for any region internationally. And this is like the most amazing, I don't know if some of you have heard of this, the most amazing data resource. Gridded population data for the entire planet from 2000 to 2020 in 5-year intervals. These are gigantic, what we call raster GIS maps. And in these data are the growth and development patterns for every metropolitan region globally. And I have my students use these data to try to understand sort of the trade-off between new development and population growth, like the rate that a region is growing sustainably. So again, you could build this kind of forecast anywhere in the world. I want to move on to a second use case. This one's a favorite of mine because it's all the rage now, and I like to think of myself as an early adopter of this one, something I've been teaching my students now for some time. And this use case is about predicting flood inundation. Specifically, the goal is to borrow the flood inundation experience from places that have experienced significant flooding, and then testing whether those experiences generalize to places that have yet to experience a major flood event. And you can imagine this would help with land use restrictions or disaster response zoning. Now, as I mentioned, this has been a big use case as of late. Here I'm showing some really amazing tools from a group, a website called Flood Factor, which is built in part from some similar methods. But as I say, I think I was early towards these tools. I started teaching this use case back in 2015 in a class I teach called Land Use and Environmental Modeling. In that class, students learn the basics of geospatial hydrological modeling and soil modeling. And we do that for 6 or 7 weeks. And that builds up to this very first geospatial predictive use case about predicting flood inundation. I put this slide up there because the student newspaper at Penn wrote an article about it, but I just thought it was hilarious. They didn't ask me about it. They used a file. This is what the School of Design looks like, where the program I run, this is the building I work in. Basically, they took a picture of the building, but they mentioned, that we were building this this algorithm, and I will show you how it works. And I think actually one of the things I'd like you to try to take away from these next few slides is that hopefully you can hear my enthusiasm for these tools, but also for teaching them, because when you hear about machine learning and data science, we often think these are engineering disciplines. But in the program I run, the Masters of Urban Spatial Analytics, we don't look for engineers. What we do is look for social scientists And my goal is to get these social science or humanities students super excited about a really complex public policy problem. And if I can get them enthusiastic about it, then I can pitch them on these, writing code, doing statistics, and hopefully I can provide a narrative over the next few slides about how it's possible to get them so excited. So we begin by showing them some overhead shots of a pretty devastating flood that occurred in Calgary, in Canada. And you can see this flood is like all encompassing. It hit the urban area. This is not in the middle of a rural area. This is in downtown Calgary. And another look at this flood is with the satellite image. Here it's sort of at the regional scale. Dark blue colors is the actual hydrology. So, rivers and ponds and streams. The light blue here is flood inundation. So that's the actual flood waters. And if you're curious, the red is cloud cover. And the goal really is to get them to try to look at this system and parameterize this system. Like, why is it that there's flood inundation over here, but not over there? And I sort of get them to sit back and look at the map, and I ask them a really simple question. What do you think, what natural or built environment features do you think helps to predict flood inundation? And typically the first response I get is distance to the river, and that is absolutely a great answer. But there are many others. And increasingly as we go through this with the class, I can see them getting more and more interested. And this is the slide that really starts to do them. I show them the slide about converting a variable like elevation. Elevation is a smooth surface across the entire region. And we talk about how to change a variable like elevation to a predictive feature like slope, and then again onto steep slopes. So here are the steep slopes that really abut the flood inundation. I make the point to them that this is how you parameterize a system, that this system, one related to hydrology, soil, and elevation, like bike share, again, it's not boundless. It's a relatively closed system that we can confidently parameterize and model. And of course, there is really one more step here that blows the student's mind, that it's actually not just steep slopes here that's important, but distance to these steep slopes that matters. And with that, we can parameterize the system for every location in Calgary, as every location has a relative distance to steep slopes. The idea, again, is if we can model flood inundation for enough cities and regions that have experienced these significant floods, if we have enough experiences to reasonably generalize from, then we can predict flood inundation risk in the next city and use that forecast to make better planning decisions. One of my favorite success stories of this is I actually had a student who took this idea and started her very own startup selling these machine learning maps to banks to help them make better, to help them better understand risks or risk in their investments. So those are two shorter case studies, and I will stop there with those examples and just list a few other areas where I think this kind of forecasting can be helpful in the context of climate change planning. The idea would be to borrow the wildfire, deforestation, crop suitability, or even something like refugee or migrant camp experiences in places that have seen those outcomes and use them to predict the probability of these events in other places that have yet to experience these outcomes. Many of these my students do in various capacities for final projects. And these are students who, we have them up and running in a couple semesters before they're building really beautiful forecasts. And again, I don't think this is the domain of mathematicians and computer scientists. These are the domains of domain experts with intermediate data science skills. And that's really the audience for my book. So, I teach city planners, but also a lot of environmental planners. I don't teach a lot of like folks with agricultural backgrounds. I would love to, but if you have a background in these domains and you have to think about, again, how to parameterize a system, this is the creative process. Like, what are the individual features that can help to explain an outcome? A computer scientist has no idea that steep slopes somehow relate to the flood inundation system, but a hydrologist absolutely does. And so this is why the book and my teaching and work in general really tries to empower domain experts and not computer scientists. So just to reiterate, the kind of forecasting that I am interested in is to borrow the experience of people in places that have experienced some outcome and test whether that outcome generalizes to a different set of people and places. And again, we're not forecasting over a multi-decade horizon. It's not about 30, 40, 50 years into the future. The emphasis is really on spatial forecasting and not on time. And if these forecasts are reliable, then I strongly believe and hope that I've at least marginally convinced you that we can use those forecasts to create some pretty valuable planning tools. And I just want to conclude, the use cases I provided here today are not the use cases that I provide in the book. Every chapter in the book is a different use case. And the ones that focus on machine learning and forecasting, they're really focused on service delivery in government, using these tools to identify who or where is at risk, typically for an adverse event in the domains you see here on the slide. And then once we've identified those people at risk, government agencies whose job it is to deliver services, these tools help them allocate those services accordingly. And in the book, I spent a lot of time talking and providing methods that can, as I mentioned earlier, test for algorithmic fairness and to develop a framework for trading off algorithmic utility and fairness. These domains that you see here up on the slide, they're important to me because they have immense social costs. So we talk a lot about health and human services, among them child welfare, which is a lot of my own personal work is in child welfare. And if you may or may not know this, like a child experiencing the emotional distress of abuse, that fear, anxiety, and distress follows that child into adulthood. And that child typically experiences subpar outcomes across a whole host of measures, which means that the social cost of child maltreatment is massive. And so, one of the main sort of theses of the book is if we can use these algorithms to identify a child being maltreated and intervene as soon as possible and effectively, we can mitigate a tremendous amount of social costs. Now, climate migration, the kind of displacement and disenfranchisement involved with climate change also has massive social costs. And, and mostly because, the scale of the problem, the millions of people who will be affected, there are also massive social costs there, like no doubt. And this is why I think coming up with proactive planning tools, using, in the case of climate change, the amazing wealth of data on the natural environment and land use and similar data sets that we have now built as a society, Planet Labs being able to image the entire planet once a day. What an unfathomable idea. We collectively as a society have this data now. And I truly believe that compared to what the business as usual approach is, that using these data to build these planning tools can help to mitigate some of these significant social costs and hopefully to help the least advantaged among us. All right, so with that, I will conclude again with great appreciation for you having me here today to chat with your team. This is a different domain than I usually talk to folks about, but hopefully I managed to carry your attention, and I'm happy to answer some questions. But again, thank you so much for having me.